2026's first Lunch and Learn Meet the Manufacturer session. Hopefully it's going to be an hour's CPD session for you, just to get help you improve some of your knowledge on a specific topic. The idea of these sessions is just to give you a bite-sized learning opportunity, understand a bit more about the company. Today it's Danfoss and the specific topic that they're talking about, which today is improving energy efficiency in building using PICV Solutions. So we are hoping to make these sessions as interactive as possible. So if you have got any questions, then please do pop them in the chat. And as we're going along, I'll try and let the speakers know about any specific questions that have come through. And if not, then there's always room for questions at the end. So thank you to Danfoss today for talking. So we've actually got 3 speakers today from Danfoss. We've got David, Oliver and Andrej. So on that note, I will hand over and let you guys start.
Thank you, Rachel. Hi everyone, good afternoon, and welcome to this BCIA Meet the Manufacturer Lunch and Learn session. My name's David Jones. I'm a key account manager for Danfoss. I look after commercial projects in the southeast, specifically in the London area. I'm also joined by my Danfoss colleagues, key account manager Oliver and product portfolio manager Andrej. So today we look at the subject of improving energy efficiency in buildings using PICV Solutions. In this presentation, we'll cover the challenges commercial buildings face with regards to energy efficiency and hydraulic balancing. We'll also look into the principles of pressure independent control valves and their place within the commercial buildings arena, as well as looking at some digital control solutions from the Danfoss portfolio. So we hope you enjoy this lunch and learn session. Of course, we welcome any questions during the presentation, or if you prefer, always welcome to ask at the end. But please, as Rachel says, put those in the chat and we'll be happy to address those. Okay, so sorry, just move on. So yes, so why does energy efficiency in buildings matter? So energy efficiency in buildings refers to the designing, constructing and operating structures to use less energy while maintaining comfort, functionality and performance. Looking at the points here, you can see just how much energy and resources are used by commercial buildings. So 12% of water use is consumed by the construction and operations of buildings. 30% of global energy consumption is caused by HVAC and the lighting of buildings. If we are to work towards reducing these figures, we have to understand that energy efficiency in buildings involves minimizing energy consumption across the building life cycle, from design and construction to operation and maintenance, but without compromising indoor comfort or productivity. So while we are looking at percentages, it's worth mentioning that only 20% of a building's lifetime costs occur during the design and construction phase. The other 80% is spent on operational expenses like heating, cooling, and maintaining the building. So this underscores the vital need to be thoughtful about the systems we design and build. By introducing energy efficient practices and modern HVAC solutions, we start to see the benefits. Personalized comfort and improved productivity, for occupants, operational excellence with lower costs, high energy efficiency and short return on investment for building owners. And also innovative solutions, easy commissioning and reduced liabilities for specifiers and builders. So here we take a look at how in 3 key stages we can plan a roadmap to smarter and more efficient buildings. In the first step, we look at upgrading HVAC performance, in turn delivering between 15 to 38% energy savings, returning an impressive 1 to 3 year return on investment. This should always be the first step due to its high cost effectiveness, paving the way for further measures. Secondly, HVAC investment on average improves the energy performance certificate, improves the EPC class by 1 for residential buildings and 1.3 for non-residential. This in turn increases the building's commercial value, improves health and comfort, as well as reducing energy costs. And lastly, at stage 3, HVAC investment alone is able to deliver the savings necessary to comply with the Energy Performance of Buildings Directive's minimum energy performance standards. Okay, so we move on to hydronic balancing, and we look at the definition of hydronic balancing and what we need to ensure to be able to achieve this. So a hydronic system is considered balanced when the correct flow rates are achieved throughout the system, not just at full design load, but also under partial load conditions. In reality, systems rarely operate at 100% load. They spend most of their operational time at part load, so true balance means maintaining control and stability across all operating conditions. Getting this right is fundamental to achieving three things: sufficient capacity at all loads, precise indoor temperature control, and maximum system efficiency. So why should we consider using pressure-independent control valves, or PICVs? In order to answer this, we have to look back at how systems were balanced in the past. As system design has evolved, so has the way we achieve hydronic balance. In traditional constant flow systems, three-way control valves were commonly used. Because flow through the branch remained relatively stable, manual balancing valves could be set during commissioning to proportionally distribute flow. Once set correctly, the system behavior was reasonably predictable. However, as the industry moved towards energy efficiency and variable flow systems, two-way control valves become more common. These improve part load efficiency, but introduce a new challenge. As valves closed, differential pressure in the system increases. This pressure fluctuation can lead to overflow in some branches, reduced valve authority, noise, and unstable control. So to manage this, differential pressure controllers were introduced to stabilize sections of the system and protect control valve performance. More recently, pressure-independent control valves, or PICVs, have become widely adopted. These combine flow limitation and pressure control in a single device, ensuring the design flow rate is maintained regardless of system pressure fluctuations. The result is stable operation at both full and partial loads, simplified commissioning, and improved control accuracy. In order to understand how an unbalanced system looks, we can use this basic but effective visual of a hose with holes in connected to a tap. The hole in the middle is our design flow we're trying to achieve. As you can see, the tap provides flow, but because water takes the path of least resistance, we have too high a flow rate at the first hole. We have too high a flow here, and insufficient flow towards the end of the run, hole furthest away. So if we run through the animation, we can see how water behaves under different demands and balancing techniques. So here we have our water hose with 4 holes in outlets, all the same size. Once we introduce flow through the hose, which represents our system, we can see straight away that because water is essentially lazy and always takes the path of least resistance, we have a higher flow rate through the nearest hole here, which of course we could think was maybe a heat emitter, but the flow reduces further along the hose or branch as it travels. If we close off the first hole or close a demand to heat emitter, the available pressure in the 3 remaining holes increases further down the hose. So we are now receiving a higher flow of water. If we close off 2 holes, again, we get an increase of flow in the 2 remaining holes. The water flowing through the hose isn't at the design flow that the system was designed to work and be efficient at. So how can we try and balance the flow more effectively? If we look at static hydronic balancing using a manual balancing valve, you can see this is great if we want to balance the flow at full load across each of the outlets. but when one closes off, the remaining 3 receive a greater amount of pressure, although the flow is evenly increased across the remaining 3 outlets. Again, if we close another outlet, we see an overflowing partial load at the remaining open outlets. Static hydronic balancing with a manual balancing valve can lead to underflow or starvation phenomena. So, proper hydronic balancing is achieved by dynamic hydronic balancing using pressure-independent control valves. When under partial load conditions, the flow through each valve remains consistent and at the set level of the valve. It doesn't increase or decrease as the pressure is spread evenly across the system and remains at the desired flow rates. As you can see, the modulating pump ramps down and is now running at a reduced speed as the excess flow of water isn't able to get through the PICV. This is also reducing the wear on the pump, as well as reducing the amount of power needed to get water around the system, increasing pump efficiency. So to reiterate that point once more, the only proper hydronic balancing is dynamic hydronic balancing using PICVs. By utilizing pressure-independent control valves, we're able to achieve perfect balancing at all loads. So here we're going to look at a quick video which just highlights some of the advantages of the Danfoss offering PICV ABQM 4.0.
Yeah, someone's just asked, is there meant to be sound with the video? Because there's no sound coming through.
Okay. Okay, I'm just going to hand over to Oliver, my colleague, who's going to present the the remaining slides, if that's okay.
Hi guys, so I'm Ollie. I'm a key account manager on our residential heating side, and to cover a bit of the sort of the commercial side where it goes hand in hand with the residential stuff. So can you hear me all right? Yeah.
Yep.
Yeah, brilliant.
Yes.
So the ABQM essentially is a 2-in-1 valve design combining control valve and an automatic balancing valve into a single body, which makes it different from a traditional. What makes it different from a traditional control valve setup is that it doesn't rely on any external balancing devices or system conditions to behave correctly. It manages all of it internally. So at the heart of the valve is the control section, which is here, which determines the actual flow through the unit. Behind that, in the actual valve body, is a differential pressure controller. That the job of this is to absorb and compensate for any pressure fluctuations in the system. As the next slide, so as the system pressure rises or falls due to load changes, of the valves opening and closing or pump modulation, the differential pressure controller adjusts automatically to maintain stable conditions across the control valve. Because of this, the design flow is set as a percentage of the valve's maximum capacity. So if the valve will do 20,000 litres an hour, it can be set to do, and you need it to do 10,000, you'd set it to 50%. So by limiting the flow mechanically inside the valve, we effectively reduce the working stroke range of the control element to only what's required for that design flow. That improves modulation quality and stability. The result is fully pressure independent flow control, meaning the valve always operates with 100% authority. In other words, the control valve has complete control over the flow at all loads, with no influence from system pressure changes, delivering accurate temperature control, simplified commission, and guaranteeing hydronic balance. Next slide. So modern HVAC isn't just about heating and cooling, it's also about delivering energy efficiently and intelligently across the whole building. Dynamic hydronic balancing ensures that correct flow is maintained at all times, preventing energy waste and maintaining system stability as conditions change. Modulating room control means heating and cooling are delivered precisely according to demand, improving comfort while reducing unnecessary consumption. And with BMS connectivity, we gain visibility and data-driven optimization, turning HVAC from a static system into an intelligent, high-performance asset. So, hydronic systems with on-off versus modulating room control. The on-off room controls operate in a simple stop-start manner, delivering full heating or cooling until the set point is reached, and then shutting off completely. This often results in temperature fluctuations and inefficient energy use. In contrast, modulating room controls continuously adjust output in proportion to demand, maintain a stable room temperature, improving comfort and reducing energy consumption by only delivering exactly what's needed. The results of this are reduced bills and consumption, higher efficiency and lower pumping costs as well, and more stable room temperature, which overall increases comfort for whoever is occupying that room. So here we have two charts, one showing on-off room control and the other showing modulating. As you can see, the on-off is over and undershooting the set point by approximately 2 degrees each side, so it's going up and down, which overall isn't efficient and generally reduces comfort for whoever's occupying that particular room. Below we have a chart for modulating control, which reduces the fluctuations to approximately 0.5 degree either side of the set temperature, which is more efficient and has less impact on the comfort of whoever's in that room. What constitutes as a comfortable temperature is individual and varies throughout the day as well. Imprecise control increases the chance of discomfort. Discomfort causes complaints and increased use of energy as people increase the set temperature to compensate for it. So they're having the temperature higher. Discomfort also decreases the productivity of an employee as well. And by stabilizing the control, the temperature can be optimized. No one is going to be turning it up or down when over or under that set temperature, and increasing the temperature setting with 1K saves 10 to 16% of energy in cooling applications. So there's also a wide variety of PICVs that all work in the same principle, but are all quite different. So things like our smaller range, which is here at the Novacon, the ABQM 4.0s, and here we have it with a Novacon actuator on it. So they're manufactured in DN15 to DN50, and there's a variety of different options when it gets to the actual valve, whether it's with high flow or low flow, internal or external threaded, with or without test plugs. There's about 30 different valve types across one small range. There's also flanged options as well, and even larger options here on the right hand side. And they all suit different actuators, so there is something for every different needed within a building. So there's actually a small video here. If you can't hear it, can someone just quickly shout out on the actual production line of these?
Can't hear any sound, if there's any sound on there at the minute.
What was that, sorry?
I can't hear any sound if there's any music playing or anything at the minute.
I have no idea how you actually turn it on a PowerPoint so that it comes through on Teams. We can skip that anyway. Doesn't matter too much. We'll send the links out for the videos that we pop in at the end because they are actually quite interesting. So the ABQM 4.0 is designed specifically to optimize the performance of the Danfoss Novacon actuators, and it creates a fully integrated intelligent valve solution. It establishes perfect hydronic balance while simultaneously connecting that balance out really into the BMS system. So we're not just controlling flow, we're making it visible and measurable as well. It provides the BMS with HVAC data, which allows real-time active energy management for 24/7 energy optimization, allowing continuous optimization rather than periodic adjustments. And with remote access, there's other capabilities such as predictive maintenance, continuous commissioning. Issues can be identified early, performance can be fine-tuned over time, and unnecessary site visits can be reduced as well, which is just overall lowering operational costs. Commissioning itself can also be carried out digitally via the actuator stroke control, rather than manually presetting the valve. This simplifies flushing, improves long-term flexibility, and makes future adjustments far more cost-effective. When setting up the Novacon in the software, you can enter the desired flow rate and the valve that it's on, and it will adjust the stroke to achieve that flow. All valves can then be open for flushing, maintenance, etc. at the click of a button. So it's drastically reducing costs in the long term. So flow control and valve characteristics ensures accurate flow control with linear and equal percentage characteristics. It also supports low flow regulation and delivers precise performance across all operating conditions. It's compatible with the BACnet and Modbus RTU protocols, providing real-time system data to the BMS system. And you've also got analog outputs of 0 to 10 volts, ohmic and analog inputs, and heating cooling change over for a 4-pipe system. It also monitors energy usage and applies advanced algorithms for optimized energy management, and it supports continuous commissioning and includes an integrated PID control of precise system regulation. So here we have the ABQM with the Novacon actuators. So it expands data and control capabilities by measuring supply and return pipe temperatures by the probes here, and calculates actual energy consumption and integrates the delta T measurements into the system control as well. It also has active energy management features, which enables optimization of the system efficiency, including minimum return temperature limitation, power limitations or regulation, and supports fair energy cost allocation across users of certain zones within a building. So we also have here an example of a system of how this would work within the building, where different valves are receiving different flows due to the demand they need. We can see here that because of the energy monitoring, the ABQM in the middle isn't happy as it's using more than 20% of 20% more energy than the others around it, and this means that it may need servicing, or there's another issue that needs identifying. So 6 reasons, things about the Novacon is it optimizes the efficiency, it provides cost savings throughout the life cycle of the building through active energy management, provides flexible flexibility throughout multiple options for building refurbishment, and is designed to suit retrofit as well as a new and fresh building install. The time saving on install as well on commissioning and the maintenance are quite high, and quite a key thing to mention here is that instead of presetting the ABQM via the spindle, the Novacon can actually be used to commission the valve, as it can adjust the stroke length based on the required flow and the valve that it's on. This also key in saving time in the future on maintenance and when flushing the system, and can also be daisy chained together as well, so that I think up to one power source can control 10 actuators. And also has advanced temperature control, which can be integrated within the BMS system. So here we actually have a cost breakdown of them. So most often HVAC investments are judged on cost side in the development phase, so the purchasing price and the installation costs. But more relevant is to look at the actual cost during the operational phase and the long-term building efficiency view. So here you can see that with manual balancing valves, they all cost about 20% in the development phase, whereas 75% of the cost of the building cycle is on the manual balancing valves. When you just change that to PICVs and actuators, it reduces it by 15%. And with PICVs and smart actuators with active energy management, it's reducing it by an overall 30%. So dynamic hydronic balancing ensures energy is distributed efficiently throughout the building and boosts user comfort with quieter operation and reduces overall energy consumption. So modulating room temperature control maintains stable comfort indoor temperatures and lets you lower heating or increase cooling set points without affecting the comfort. And this then therefore enhances the system efficiency and helps save energy. So here we have a breakdown of what is actually in the actuator range and where they actually come with in terms of the new building automation and control standards. So things like the Novacon actuators are in band A, smart TRV sensor in band B, and regular TRVs or thermal actuators or standard ABQM actuators are in band C. And then when you look at it from the valve point of view, that the dynamic balancing valves are in band A, and as you go down, you get back down to like regular TRVs and manual balancing valves. And just sort of a slide on where these actually fit within a system. So the solutions for both heating and cooling aspects. I think that's it. Is there any questions?
Hi.
Hi. Oh,
What's
sorry.
the difference between a PICV and a smart valve?
What do you mean?
I tried to do a little bit of research before the meeting, and it was just there were two things, and I wasn't sure whether they were same thing or.
So the two separate products. So PICV valve is essentially the valve that the actuator would go on. So you can have a PICV valve with quite a generic, maybe a thermal wax actuator, which is literally just on off. It isn't modulating and has little control. Whereas something like a smart actuator, you would actually put on the PICV valve, and you could then. There's a lot more that you can do with it. Does that sort of answer the question?
Yeah, as I say, I'm a training administrator, so I'm just trying to get a better understanding. And I thought, right, that's great. Thank you.
You're welcome.
For some of the people who are listening who are on the facilities management side, what are some of the most common mistakes that you see in terms of how they've been fitted, or is it more about the monitoring where you see more problems? Or
I think water quality is quite a big one, but I think we have done quite. I think Andrej will be able to tell a bit more about that. What you guys have done in Slovenia on that, particularly with the calcium buildup.
oh yep. So someone's raised their hand. Jordan, I don't know if you want to put your unmute yourself and ask the question.
Yeah, sure. Hi guys. I think I had two questions just on the Novacon kind of section, it looks like that there's a variety of information that you can pull from the actuators in terms of the performance of the valve, things like flow and energy monitoring. So I'm working on a lot of schemes at the moment where we might have like neighbours requirements, or like requirements to monitor energy from things like heating coils and things like that. So interested to know energy monitoring capabilities of the PICVs. And then secondly, I work in the business where we would like size and select these valves on new build projects. So are Danfoss able to provide any assistance in the kind of pre-construction element in terms of sizing and selecting the right type of valve and applications?
Yeah, 100. So with the design and building sort of side of it, we do actually have a service where we can take the flow rates and go and say and allocate the correct valve to it. So that is something we can do. As for the Novacon question, I'm not sure if Andre might know a bit more about them than me.
Yeah, for sure I can help. Regarding, you mentioned Design Support Center. Yes, we have a group of designers supporting you directly on your project. They can calculate the pump head, they can calculate the pipes, pressure drop settings, select the valves, etc., together with the codes, actuators, whatever needed. So it's a full offer, as well as they can make a comparison between different solutions. I think this is really good support, and I'm sure we can share the context, right? Regarding the Novacon, yes, Novacon was designed to be, I would say, very smart, right? It's not only sending the signal to the valve, it's also receiving it, right? So the fact is that I would say the main benefit along with the data management is also that all is connected via BMS. So no climbing the ladders, do the pre-settings, opening the valves for flushing, etc. This can all be done via BMS. And it will also detect if anything is either blocked or clogged. This will be actually alarm sent via Novacon. And now going to the I would say management of so-called energy allocation, right? Novacon is smart, and it can detect from the position of the valve at what position, since the valve is perfectly linear with very, very good control performance, it will actually detect the flow, and it will send you the flow via BMS. This, Oliver, you showed before, right? Where you can see, okay, among the 10 fan coils on the branch, one is using 30% more. Why? This is then alarm for you to go and check, right? This is one, and then we have more, I would say, energy functions, so-called delta T manager, where you can set the fixed delta T, and then the Novacon will control the flow to achieve or to keep this delta T. This is one. Then delta or power manager, where you do similar things, but you say, okay, I want to have always 2 kilowatts here, and it will keep the flow according to this power. I would say we have quite a lot to offer via Novacon. And I'm more from the valves world, but I'm always saying that with PICV, with ABQM, we fixed all the hydronics issues, hydronic balancing issues, and with the perfect control on the control valve, together with Novacon, we offer all on the digital side as well. Together it works as a perfect solution.
Thanks, Andre. Can I just interject? Jordan, myself or Oliver, more than happy to visit premises and do a more specific Novacon presentation if there's anything else you need to know on that, but also support, as Andre mentioned, and Oliver within our design team, which can take your schematics or your project requirements, and we can develop that and turn that into schedules and schematics for you as well.
Okay,
Yeah.
cool. So I think, yeah, probably two things then. Firstly, the if you have like a data sheet, particularly around the energy monitoring and the information that can be communicated to BMS over the ABQM Novacon modules, that'd be great. And then we've got an office based in Houston, so yeah, potentially I'll reach out to you separately and maybe have a sort of show and tell with some of my colleagues.
Okay, that sounds good. No problem,
Yeah.
Jordan.
Cheers, guys.
Thank you.
There was someone else who had their hand up. I think they've put it down now, but I don't know if you've still got another question. Then please do feel free to unmute yourself and ask the team. I'm sure they'd be happy to answer if you've still got a question.
Sure. Sorry, I was a bit late to the call. Is actually regarding hard water and building up skills within the system. First of all, I would like to ask whether you've came across problems such as hard watering and building up skill within your system. And second, would your valve somehow indicate some sort of friction due to the build-up skill within your valve? How you normally tackle this issue?
If I may answer, I was a part of 4.0 project. We as a solution provider, or I would say valves manufacturers, we don't necessarily have an impact what's actually the water quality in the system, right? So for us, and we studied this, I would say, for years, we have two challenges in the valve actually. One is the control valve, and one is the DP controller, since PICV consists of these two components. How we tackle these challenges, right, is that we change the material of the control valve cone. We're using high performance polymer, where when you meant hard water scaling, you meant calcium carbonate, right? This is usually the biggest pain we cannot avoid. And with using this material, we are reducing the surface actually is less convenient for scaling to be made on the surface. This is one. And then the most important is actually DP controller. This is the moving part. And with the design of small ABQMs, 15 to 32, on bigger, it's not a problem. We actually change the design that we have this moving part without dynamic o-ring. Dynamic o-ring means with the time you are losing the grease and friction increases. So the challenge is always friction, where it means different performance then, right? So in this design, we are not using dynamic o-ring, which means also we proved with the tests that the performance is not lost by the time, also in the hard water conditions. How to achieve that? Yeah, with a couple of, I would say, a couple of additional months in designing, because it's a big problem. And also the idea was that we built in the department where I am, when we're designing the valves, we built the performance rig, where we were actually testing the valves with really hard water, calcium carbonate at 90 degrees for a couple of months, and then we perform the measurements and see what's observing. At the end, we improved the design so far that we didn't see any changes on the performance after being installed in really hard conditions for a couple of months, which is, I would say, in reality, because we need to speed up the test, right? We simulate with the cycles. So when the valve is new, 50,000, 100,000, 150,000 cycles, which means full opening and closing in hard conditions, water with full of calcium carbonate. And with this, we simulate with 50,000 cycles, let's say 2 to 3 years in the real application, with 100,000 cycles, 6 to 7, and with 150,000 cycles, up to 10 years in the real application.
Thank you so much. I just wonder whether we will be able to capture that, any notification or indication of building up scale within the valve from the data we receive.
Very good question. We test also different solutions available on the market, and what we have seen as a result of, let's say, valve being filled with calcium carbonate is reducing the nominal flow. It cannot achieve the flow anymore.
Okay, sure.
This could be quite substantial, up to 40–50% after, let's say, 100,000 cycles.
Okay, thank you so much.
You're welcome.
Yeah. So I don't know if that was that the end of the presentation, or was there a couple more slides to share, or?
No, that was it.
Yeah, okay, perfect. So thank you very much everyone today for taking the time to join the session. What we'll do is I'll drop everyone an email with a copy of the slides, and I'll make sure that the team from Danfoss are copied in so you can reach out to them if you've got any further questions.